had no refreshing power. So so how about instead a riddle? What has 2 eyes, 3 noses, and 6 ears? 6 ears, yes. Anybody? The answer is a monster. Anyway, okay, thank you. Okay, yeah, so yeah, I'm Latham Boyle. I'm a physicist from the Perimeter Institute, which is in Canada. And I'll be telling you about 2 recent papers in collaboration with Shane Farnsworth, who will be speaking after lunch. He's also at Perimeter. And I should emphasize right at the outset that a lot of the key ideas here are due to Shane, and I'm his expositor. So yeah, let's see. So the idea of what I want to explain is the following. That well, let's say I'll give the outline for the talk. The outline is first I want to just very briefly give my own encapsulation of the same thing that's been reviewed very nicely and in much greater detail this morning by Fidele and Christoph. Basically, Kahn's approach to the standard model. I want to give the sort of 3-point bullet point summary of what's going on there. And then I want to give my 5-minute sales pitch. Why? So I think there's a lot of different people who are interested in Kahn's approach to the standard model come to it from different motivations. And in particular, when I've heard talks by him, the motivations that he gives, the reasons that he finds it compelling are, not the main ones that I think are interesting. I will give you what I think is the argument that should be presented to the bread and butter physicist like myself, that there's something interesting going on here. That it is not just some complicated reformulation of the standard model that's ultimately equivalent, but just harder for physicists to understand. That there's something that has been discovered here, that in a non-trivial sense it's getting more of the structure of the standard model out for less input. Okay, so we'll give a head-to-head competition between the standard algorithm for writing down the Lagrangian for the standard model, Kahn's algorithm. They'll fight. We'll see who wins. We'll see who's okay. So then. And now I should also say I want to give that at the outset to motivate things, but I also want to be brief. Now this is sort of something where I can imagine there might be a lot of people who want to discuss this or ask questions about it. So I'm going to try to leave time at the end to discuss this and argue about it if you want. So I'll just try to be brief about this, but I don't want to spend too much time here because mostly I want to try to introduce our result. That's not how the result is spelled. Our result. So our result is basically that, in short, the idea is that the normal starting point for Kahn's construction of the standard model is a spectral triple, a real spectral triple, so it's equipped with some extra operator J. So I want to give you arguments both mathematical and physical so basically what I want to say is that this data naturally fuses into a new object, an algebra that we call B. And I want to give you both mathematical and physical arguments that B is really the more fundamental object, the basic object you should be thinking about, that the axioms, that what were a long list of axioms and assumptions here become greatly unified and simplified over here. And that furthermore, in terms of the physical output, the physical algorithm, things that were unexplained, things that had to be put in by hand over here, Most things did not, but there are a few important unexplained things that have to be essentially fudged in the normal approach that get fixed from this standpoint, and then that will be explained more in Shane's talk in more detail. And then at the end, I want to say, that's right. So this algebra is no more unique than the possible spectral data that you can put in, but given the spectral data, there's a way to construct this algebra. I'll explain that more. And then, open questions and problems I want to mention. I don't want to give the impression that everything is that life is perfect. Hopefully Christoph already convinced you of that. There's plenty of things still to puzzling things still to figure out. Okay. So my 3-point summary of Kahn's approach to the standard model, and by the way, I should say I'm always, as a shorthand, going to say Kahn's approach to the standard model, just because that's what I say. But Fidele's, certainly I want to steal actually Fidele's slide for future talks and get a also rundown of it. He knows the history of the subject much better than I do. But anyway, as Fidele made, what? As he explained clearly, there's really a lot of people who have contributed a lot of different things to this approach. So anyway, so my apologies for always, as a shorthand, saying it this way. So Kahn's approach to the standard model proceeds in 3 steps. Step 1, you choose a geometry that satisfies some set of axioms and assumptions. Once you have a geometry that works, there is a crank you turn to quote-unquote fluctuate the Dirac operator. So you fluctuate D, you turn it into some new operator, sometimes called dA, which is equal to the original D plus some connection terms. And Kahn gives a formula for what this, given this data, you compute this extra bit that you're supposed to add to D. Now, morally speaking, this is what's going on here to a physicist, is that you're taking an operator, a derivative operator that is not covariant, and you're adding some connection terms to it to make it into a covariant derivative operator. But in what exact sense you're doing that, and covariant with respect to what exactly, has not been quite clear. That's one of the things we want to say. That's one of the things we want to say that we will clear up a bit. And then finally, once you have your fluctuated D, you compute it. There's a function, the spectral action, that associates a real number to it. Okay, and that function looks schematically, well, more than schematically, like there's a first term, which is some weighted trace of D, and then there is a second term, which is the expectation value of D with respect to some element psi of the Hilbert space. And when you compute, the basic idea is that when you use the heat kernel expansion, if you choose the right non-commutative geometry to start with, turn this crank, plug into here, and expand this formula, you find that you get a formula which almost exactly matches the standard model, with the 2 important discrepancies being that you get constraints on the parameters so that the Higgs mass turns out wrong, and there's a constraint between the 3 coupling constants, which does not quite agree with experiment. That's what Christoph explained in his talk. But basically, you expand out, and you get this long formula for the standard model. All of the bosonic terms in the standard model, all of the terms that only involve bosonic fields come out of here. All the terms that involve fermion fields come out of that second term. And so just to preview what our claimed results are, again, basically, our results can also be categorized by these 3 points. Here, instead of this original input data, which satisfies a rather long list of assumptions and constraints, I'll explain how you construct from that an algebra B, in which the number of assumptions and axioms becomes, you can state them more succinctly. They basically boil down to many of them boil down to the statement that B is associative. So you construct this algebra B, which a priori will not need to be associative. But when you impose that it is associative and equipped with a star operation, you get back a long list of the traditional axioms and assumptions here. So then here, as I said, this formula, we have a different argument about what's going on here, how you decide what connection terms to add to the Dirac operator. From a physicist standpoint, it's just nothing but the statement that you make the Dirac operator covariant with respect to what? With respect to the automorphisms of B. So that's sort of the second important point. And then the third important point is a physics point. If you take the geometry traditionally used to describe the standard model, you construct B, you take D to be covariant with respect to B, and then you ask what is the corresponding physical output? What are the predicted particles? Well, it turns out you get back the standard model fermions and gauge bosons and scalars with the right charges, which is the same as the usual story. But you predict that there are two extra particles. There's an extra symmetry, first of all, which is not present in the ordinary standard model. An extra U1 gauge symmetry, which is gauged baryon minus lepton number. And associated with that, as a consequence of that, there's 2 additional particles. There's the gauge boson, B mu, which carries that mediates the associated force here. And then there's a new scalar field, sigma, which is very similar to the scalar fields that have been discussed by in Fidele's talk. He gave one mechanism to produce an extra scalar field like this for the purpose of solving the standard model Higgs mass discrepancy. And in the work that Walter and Kohn and Shamsuddin have done, they have another mechanism for producing this field sigma. The field we get is very similar to theirs, with the difference that, also as Christoph was describing, he has a variety. He has had several models where you produce extra scalar fields, or in particular a scalar field quite like this. That's a singlet under the ordinary standard model gauge group. Unlike the Fidele's group and Walter's, this guy will turn out to be a complex field, not a real field, and it's a singlet under the ordinary standard model gauge group, but it is charged under this additional U1b minus L symmetry. Okay. Okay. So now I want to give my head-to-head competition between the standard algorithm and Kohn. It's kind of, well, in this case, normally, it's interesting. I mean, maybe yes. You know, normally you don't think of this of the dilaton as carrying gauge charge, but who knows? I mean, okay. So the standard route for writing, you know, so there's this Lagrangian, the Lagrangian for the standard model of particle physics. It's this long formula. But the question is, what is the minimal data I have to tell you in order for you to go off and write down that formula on the nose? You know, I don't have to give you the whole formula. I can give you some smaller set of data to specify it for you. So what is the standard approach to giving you that data? According to the standard approach, there's 3 steps. First, I tell you the symmetry group. So I tell you the group G. So in particular, the gauge group. For the standard model, I tell you it's SU3 cross SU2 cross U1. Okay? And once I've told you that, I've told you what the gauge bosons are. Because for every generator of these groups, Yang-Mills theory forces you to have a gauge boson. So for example, there's SU3 is an 8-dimensional group. So you have 8 gauge bosons, and and their transformation properties, they have to transform in a certain way. They have to transform as the adjoint. Transform into one another as the adjoint of SU3. Okay, but I haven't told you anything yet about what fermions are present, what scalar fields are present, and how they transform under this gauge group. So step 2, I have to tell you the fermions. Okay, and the way I tell you, I have to make a list of what fermions are present and what their representations are. Okay, and so I give you the following table. So here along the top of the table, we have the gauge groups, SU3, SU2, U1. And then I list the fermions. So there's the left-handed quark doublet, the right-handed up quark, the right-handed down quark, the left-handed lepton doublet, the right-handed neutrino, and the right-handed electron. Those are the fermions that you're going to include in the theory. And now, as Christoph explained, this is actually just one generation of fermions. For some unknown reason, there's 3 copies of this generation in the standard model. So secretly, there's really just whatever I'm about to write, you take 3 copies of it for who knows why, for some unexplained reason. And then, so that's the list of the fermions. That's an additional input. And then how do they transform under these different groups? Well, another input I give you is that the quarks all transform as triplets under SU3, 3-dimensional representations. The leptons all transform under the trivial representation. Then under SU2, another input is that the left-handed fermions transform as the 2-dimensional representation of SU2, while the right-handed guys all transform as the singlet. And then finally, I give you some weird list of U1 charge assignments. Basically, this is like electromagnetism, but it's so-called hypercharge. It's a related. Anyway, so they have some particular charges: 1/6, 2/3, some odd list, -0.5, 0, -1. Okay, so that's step 2. I tell you the fermions and their charges. But then I'm not done yet, because I still haven't told you what the scalar fields are. In the standard approach, that's a completely independent approach, a completely independent input. Okay, so I have to continue this table and list for you all the scalar fields that are in the theory. Well, in the standard model, it's an unexplained input to the standard model. But I just declare there will only be one scalar field. Even though there are lots of fermions, for some reason there's only one scalar field. And I tell you it has these particular charges. It's a singlet under SU3, a doublet under SU2, and it has a particular hypercharge of 1/2. Okay? So now in Kahn's approach, so once I've told you all that information, I just say, there are the fields. Those are the representations they transform under. You're now instructed, go off, write down the most general function you can build out of those fields that is invariant under all of those, under the gauge group SU3 cross SU2 cross U1. Bang, you get the standard model of particle physics as the result. Okay, so in the standard approach, that's the tightest way that I can present the information to you so that you can go and, that's all the input you need. Well, well, which are there, but just have poor constraints. I mean, they probably are there at some level. It depends on whether you think you could also say that the theory is renormalizable, or like you said, you could say it's an effective theory with all those terms included. It's just that their coefficients, they all have, every term comes with unknown coefficients, and they're all small enough, presumably because some more fundamental energy scale is high enough that they're all small enough they haven't been detected yet. Okay, now in Kahn's approach, so step one is you pick an algebra. Now secretly, picking the algebra is really parallel to this first step because, roughly speaking, the symmetry group of the theory that you get out at the end of the day will be the automorphisms of A. Well, really, I'll tell you later that it's the automorphisms of B, but roughly speaking, it's the automorphisms of A. Okay, so over here we had to put in the symmetry group. Over here we really put in the symmetry group as well. So far the game is tied. Now the next thing we have to do usually is to specify the representation of this algebra on some Hilbert space. So we give some matrix. I won't write it here. Shane will go through it in detail in his talk. But well, I guess you didn't quite see it in Fideli's talk. But anyway, there's some 96-dimensional matrix that says if I choose an element of the algebra here, how do I encode that as a matrix that acts on the Yeah. Right. Right, which is also why I'm not doing it. Yes, exactly. So anyway, you give a 96 by 96 matrix which specifies the representation of this algebra on the Hilbert space, and that is exactly analogous to giving the Hilbert space is nothing but the Hilbert space of fermions. So that ends up giving you this information, the information about how the automorphism group of that algebra acts on the fermions. But here you begin to pull ahead a little bit because here you're representing, on this side you're representing a group, on this side you're representing an algebra, and as explained in various papers and from various ways, representing an associative unital algebra is a tighter process, more restricted process than representing groups. So for example, over here it's an unexplained input. So these are Lie groups. They have an infinite number of irreducible representations. So for example, SU2, there's the singlet, but then there's also a 2-dimensional representation, a 3-dimensional representation, 4-dimensional, 5-dimensional, etc. What? Yeah. And in every dimension there's a representation, and so it's an unexplained fact about the standard model. Why is it that it happens to be that all the inputs that all the fermions under all of these gauge groups are either in the singlet or the fundamental with respect to the gauge group? Okay, on this side that's an explained output of the model. That ultimately follows because the fundamental thing we're representing is an algebra, and the gauge group just emerges as the automorphism of that algebra. Okay, and there's this nice paper in 1997 by Krzyzewski, which I would start with if you're interested in that point. But and then there's these more recent classification papers by Christoph and collaborators, and by Kahn and Shamsuddin in 2007, 2008, which you get more than that actually. But anyway, the point is you do better already at step 2. But then the real killer is step 3. There is no step 3. Okay, once you specify the algebra and you specify its representation on the Hilbert space, which is analogous to giving the group and the fermionic representation, there is no additional step 3 where you have to specify the list of Higgs bosons, the list of scalar fields and their representations, because the Higgs bosons are in some sense reinterpreted as another component of the gauge boson. So just like up here when I gave the group, that was enough to determine what were the corresponding gauge bosons and their representations. There's something analogous here. Once I give the algebra and its fermionic representation, it is a matter of turning the crank okay, modulo minor details that I'm ignoring, but that I'm not ignoring. I'll explain more later, and Shane will explain in much more detail in his talk. But to a 0th and 1st order approximation, let's say, once you give the algebra and its representation, you turn a crank and determine what are the gauge bosons and what are the scalar fields side by side. Okay, so he really is giving significantly less input for the same output Lagrangian. Okay, so that's if you're trying to sell the thing to a physicist, that at the moment, and hopefully in the future, there'll be a new prediction from the approach that will have, a new prediction for some number. You go up and measure that number, and you get it correct, and the other guys didn't predict that number. That will be the thing that will really convince a physicist. But if you want to tell the physicist right now, today, what is the reason you should be paying more attention to Kahn's approach than you currently are? To my mind, this is the best argument. Okay, and so now I want to go on and explain, move on to discuss our this algebra B and what's, yeah. Okay, so basically, well, maybe should are there any, I was kind of, somehow I feel like it's a natural point to stop for questions, although I had also just encouraged you guys to hold your questions for the end. So I'm sending mixed signals, but one not too highly combative question would be permitted. No, nothing. No, they're all too combative. Okay, so okay. All right, what did I do with my? Okay, so as I say, I want to explain why we switched from the standard formulation in terms of a spectral triple turned into a real spectral triple with the addition of J, why we switched attention to defining this new algebra B, and what is B, and why do we think B is the more basic object? So originally when we started working on this, we sort of naively thought that everything about the standard model was completely understood from this approach. We hadn't yet totally gotten into the nitty-gritty of it and understood that there were still things that remained to be hashed out and still problems. We thought everything was understood, so we wanted to go beyond the standard model. We wanted to see if you could it's something other people have tried to do also. If you could do so-called grand unified theories within this framework. And I don't want to get too much into it, but anyway, there's you basically you're not going to be able to do grand unification with an associative algebra A. If you take your algebra A to be associative, because the available representations do not match the known representations of fermions that work in grand unified theories. They're not available to you. They're available as representations of groups, but not as representations of unidal associative algebras. So we're like, okay, we have to work with some non-associative algebra A, but how do we rephrase Kahn's formalism? There are a lot of places along the way where it seems to be phrased for an associative algebra. Places that don't seem to make sense for a non-associative algebra. So how do we rephrase things so it continues to make sense in the non-associative case? And the first basic stumbling block is that, the basic starting point here is that you take this algebra and you give a bi-representation on H. Okay, there's supposed to be some linear representation of A on H, a so-called left action and also a so-called right action of A on H. What does that even mean for a non-associative algebra to represent it that way? Because I mean, if I represent, in the finite dimensional case, let's say if I represent, what I usually mean by representing is I map each element of the algebra to a matrix that acts on the Hilbert space, but then matrix multiplication is associative, so how will I possibly preserve the non-associativity of the algebra? Well, turns out there is a beautiful answer to this question of what it means to represent a non-associative algebra due to Eilenberg. Samuel Eilenberg from 1948. And it is the following. You say, okay, suppose I have an algebra and I want to define what it means to bi-represent it on a Hilbert space H. Okay, well first I define some left action of A on H. So here I just mean some bilinear map from A times H. So here I'll always use A to mean an element of the algebra A, and I'll use H to mean an element of the algebra of the vector space H. So this is supposed to be, this is some bilinear, this denotes some bilinear map from A times H into H. And then I have also, I'll define a right action, which a priori is just another independent bilinear map from H times A into H. And then Eilenberg says, okay, the way we define a representation is we just define it to be a new algebra B. Let me call it B naught for now, because B, we'll see, will be something slightly different. But we'll define a new algebra B naught, which is just, well, at the vector space level, it's just the direct sum of A and H. And then to turn it into an algebra, I need to give you the product on this algebra. So the product will be, if I take two elements of B naught, let's call them B and B prime. Well, because it's the direct sum, I can write it as each element. I can write B as A plus H, and B prime as A plus H prime. And then if you just expand this out, the first term you get is A times A prime. Well, that'll just be the product inherited from the algebra A. The next term I get is A times H prime. That product will just be a product into H, defined by this left action. Then I get H times A prime, this times this, which will be defined by my right action. That'll be another element of H. And then I'll just define the product of H times H to be 0, H times H prime to be 0. Product of any two elements of H is 0. Okay, so why are we defining this to be the representation? Well, the point is that if we then demand that B naught is associative, then this algebra, the definition of this algebra, reduces to everything you usually mean by an associative bi-representation of A on H. Okay, so let's just spell that out. So it'll be helpful to define the associator. Okay, the associator of any three objects, it's just like you define the commutator of two objects A and B to be AB minus BA. The associator of three objects is AB times C minus A times BC. In other words, the product, but with the parentheses and the two possible positions. So if an algebra is associative, that's equivalent to saying that all of its associators vanish. Exactly. That's what I was going to say. No. So let me just explain the logic again. The logic is, Eilenberg's logic is the following. If you have a left bilinear and right bilinear operation defined of A on H into H, and A is not assumed to be associative. Exactly. He says, let's define the representation of A on H, the bi-representation of A on H, to be this algebra. Now, why would you even call this thing the representation? Because, in the case that you assume B naught to be associative, you recover all the usual assumptions you make. In other words, so just to be clear, so if you assume that B is associative, you recover, like you say, first of all, if you take the associator of three elements of A, that recovers the usual, that recovers the standard assumption that A is associative. If you take, yeah, then another associator you consider is two A's and one H, with the H on the right-hand side. That's exact. Yes, exactly. Well, this guy says that A is, this is exactly what you usually mean by A is left represented on H. This associator, the one where you put H on the right-hand side, on the left-hand side, I mean, this says that A is right represented on H. And then the one where you put H in the middle, this is saying that left and right actions commute. So this is what is often called the order zero condition by Kohn in the literature. This is the order zero axiom. Okay, so we're beginning to see the structure of the argument that we're gonna construct. So you have in terms of B you have one assumption, but it gives you here a list of 4 of your traditional assumptions that A is associative, that it's left represented on H, that it's right represented on H, and that left and right, those left and right representations commute with each other. Okay, so let's take that as a hint and proceed and see if more things come out. What? That I don't know. That I don't know. To be honest, I learned about this. But I mean, because what do you mean? Because this algebra B naught, this algebra B naught is perfectly well defined, even if A is non-associative and B is non-associative. The fact that it reduces to the associative definition when you take B naught to be all the associative assumptions when you take B naught to be associative is why you call this thing a generalization of the notion of an associative representation. You know, understand what I mean? So, for example, so Jacobson and various people in the 60s tried to classify all the representations of alternative algebras and Jordan algebras, and there, A would be a non-associative algebra, a Jordan algebra, or an alternative algebra, and they would ask, what are all the possible Jordan or alternative algebras B that we can construct in this way? That's true. So just like the associative case isn't the fully general case, those cases are not. That's right. That's right. That's right. That's right. I didn't consider anymore every other associator with 2 or more H's trivially vanishes. It vanishes because of this product rule. So you don't get any. Demanding associativity doesn't give you any other conditions. Only these 4. Okay. In fact, let me number these 1, 2, 3, 4 because I'm going to keep count here. Okay. So far I've just described representing A on H, but you know, really in Kahn's, really it's not enough to just represent A, the 0 forms on H. We want to represent 1 and higher forms on H, especially representing 1 forms is key for the physical construction of the spectral action. So we have to not just so at this point the next point in the construction is to so far, no J. That's right. It'll come in a minute. So J will come when we put in a star operation on B. Okay. So the next thing I want to do is go from A to the. I want to define the universal differential algebra of forms over A. Okay, and this is a standard construction I learned about from Landy's 97 introductory book. The only difference is that, well, I'll explain it in a second. so how does the construction go? The way I would phrase it is as follows. For every element A, I just introduce a formal symbol dA, and then I generate the algebra that I can get from writing down products of A's and dA's. So, for example, I could write down an element like that. And I mod out by a few relations. Okay, I mod out by, I assume this thing is linear in this sense. And Leibniz. Okay, and other than that, let me just generate the general algebra that I get from these two guys using nothing but the product that I know of on A, the algebra I started with, and modding out by these relations. In particular, as described in Landy's book, we're not going to assume anything about commutativity of A with dA or dA with dB. Nothing about that. And then we go a step further. We're not going to assume anything about associativity. So apart from whatever we know from the algebra A itself. So in particular, we're not going to assume that dA, dB, dC associates, or that any product like that associates. Okay. Say it again. That's right. That's right. So sorry. That's right. I'm back to the way I want to present things is exactly analogous. The way I want to present things is exactly analogous to what Eilenberg does. He builds an algebra that makes perfect sense in the non-associative case, when everything's non-associative, and then he says, okay, if I impose associativity now, I get 4 of my original assumptions that defined what I meant by a module. I'm going to say something similar. I'm going to build an algebra B, very analogous to his algebra B naught. It will be defined in the non-associative case, but then when I impose associativity, now I'll get a considerably longer list of the standard assumptions back. Okay. So omega. So let me assume for now that neither A nor omega A is associative. Nothing is associative. Okay. So, but nevertheless, this algebra still has a natural grading associated with it. Okay. Yeah, do you agree with that? Okay, sorry. That was a dramatic. So, for example, an element of omega 2 would be AB times DC. Let's say A times D of B times C. Okay, with the parentheses there, that's an element of omega 1 of A. Okay. So now I want to represent that algebra on H. Well, I just use Eilenberg's trick again. I need to define some left action. If I take any element omega in omega A and any element H in H, I want a left action of omega on H that is an element of H, and I want a right action of omega on H, which is an H. And then I define the algebra B to be exactly the way Eilenberg did. I define it to be the direct sum of omega A and H equipped with this product, same product we had before. Omega plus H, omega prime plus H prime is, you expand it, the product inherited from omega A, the product, the left action the right action, and 0. Sorry? So at the moment, D does not extend onto H, but indeed it won't square to 0 on H, right? Okay. So that's what I want to say. I want to make two remarks here. One is that this algebra is graded in two different ways. Okay. On the one hand, you can assign this grading 0 and grading 1, and according to this product, that's a consistent grading for this algebra. So it's a super algebra. But there's a more refined grading. You see, there's this grading you can assign. You can keep this grading on omega A. So this guy breaks into a 0 graded, 1 graded, 2 graded, etc. part for all finite n. And then according to that grading, this thing has to be assigned grading infinity. Okay, so H, according to that grading, H is reinterpreted as somehow omega infinity of A. So why I say that is because according to this product, any finite form times the infinity form is an element of H. It's an infinity form. So any finite number plus infinity is infinity. So that's the consistent value that has to be associated there. And so now if I want to extend D, okay, so there's this standard construction that extends D. We introduce D as a symbol on A, but there's a standard construction that extends it to omega A, and it's a map. It's a Leibniz map from omega m of A to omega m plus 1 of A. If I want to, but now really, if the fundamental object is B, not omega A, I want to extend this Leibniz map to the whole of B. So I need an operator that goes from omega infinity to omega infinity plus 1, which is infinity again. Okay, so I want to say item 5, I'm led to introduce here an operator D from H to H, which is nothing but the name I call the map from D from omega infinity to omega infinity plus 1. Now, if I demand that it's Leibniz, it's easy to check that if I demand that this extended D is now Leibniz on the whole of B, not just on omega A, I get two additional normal assumptions, which are that the left action of a 1 form on the Hilbert space is given by the commutator of D with the left action of a 0 form, and the right action, and there's a similar form for the right action. The right action of a 1 form is equal to D with the right action of a 0 form. Oh yeah, thanks. Sorry. Thank you. If I take the fact that now again, if I want to impose now, I want to take as my assumption that B is associative. So now, in addition to recovering these first four guys, there are some other associators I can consider now. I can consider the associator of any 3 elements of omega A. That implies the usual assumption that the algebra omega A is associative. If I take 2 omegas and an H, that implies that it's left associated, that it's left represented on H, that omega A is left represented on H. Is that clear? If I consider this associator, if I take that to vanish, that says omega is left represented on H. If instead I consider this associator, that says omega is right represented on H. If I consider this associator, okay, so if I consider the associator between, remember I already considered the associator between the elements A are really the 0 forms here. So I already considered that a left and right action by a 0 form associate. That was the order 0 condition. The order 1 condition is the statement that a left action by a 0 form and right action by a 1 form associate. Okay, so that's the standard order 1 axiom. And then notice at this point that there's a lot of other associators that we're not including here. There's omega m, an m form on the left, according to this prescription, should associate with an n form on the right. Those are not traditionally imposed as axioms in Kahn's non-commutative geometry. They're sort of higher order conditions. What Shane will explain is that we were worried when we realized there were these extra axioms. We were like, oh, crap. You know, we're going to impose this. It's going to kill Kahn's standard model geometry. We thought it was going to kill it. Another possibility is that it would be automatic, that there would be no additional constraint. The answer is neither. The answer is beautiful. The answer is that it does give an extra constraint, which exactly sets to 0 seven unwanted terms in the model that previously had to be set to 0 by an assumption made up by hand. It's related to what traditionally you have to assume as an empirical thing you want, that all the terms that would spontaneously break SU3 color have to be set to 0. Those terms, for example, get set to 0 by these extra axioms, but none of the terms that you want get set to 0 by the additional axioms. So that's another important bit of evidence in favor of this approach. But just to push on, I just want to rattle off. Okay, so now the next thing I want to do is I want to say. So far, all we've done is introduce B and ask what is implied by it being associative. I want to say there's a bunch more conditions, a bunch more of the traditional assumptions that you get back by saying that B is equipped with a star operation. In other words, an antilinear anti-automorphism that respects its grading. Okay? So if I just assume that B is equipped with a star operation that has those properties, well, to respect the grading, it has to be like this. It has to be like if I write B as omega plus h, an element of B is omega plus h, the star has to be somehow omega star plus jh. In other words, this star operation has to respect the grading on omega a. So it takes so the star of an M form is another M form, and this guy has to be there has to be some antilinear operator on H, so that maps H to H. So I'm forced to introduce J, so I want to count that as an additional point for this approach. Okay, and then if you demand that it's an anti-isomorphism, like you do normally for a star operation, so that BB prime star is equal to B prime star B star, that gives you the standard assumed relation between left and right action, that right action of A is equal to J, left action of A star, J star. And it applies that omega A is equipped with the usual star operation. It also implies a new thing, which is a relation between the left and right action of higher forms. This is a relation between the right action and left action of zero forms. But there's a similar relation implied for any, which is not normally taken as an assumption, but is perfectly as an axiom, but is perfectly consistent for any higher form. Well, you know, there's the yeah. Anyway, there's a sign that I don't agree with about that, but we can discuss that afterwards. So I guess that maybe roughly speaking completes my list. I want to say you get a lot of traditional assumptions, including a lot of traditional assumptions, including a lot of the traditional axioms, but also sort of assumptions that you don't normally write down in a list of axioms. Okay, and then you get crucially you get this additional constraint, number 10, higher order conditions, which set to zero terms that otherwise you have to set to zero by hand in the standard model, and without setting to zero any terms you didn't want to set to zero. So now I just want to mention there's also an interesting reinterpretation of the KO dimension table. So there's this normal table of these three symbols, epsilon and epsilon prime and epsilon double prime. And depending, so these three values take the value plus or minus 1. And so epsilon, if epsilon is plus or minus 1, that's telling you about does j squared square to plus or minus 1. That sign is epsilon. Epsilon prime is telling you does j commute or anti-commute with d. And epsilon double prime, so this sign is j. This sign is epsilon prime. And this sign, whether it commutes or anti-commutes with gamma, is epsilon double prime. Well, those guys have a natural meaning, reinterpretation in terms of these guys. So first of all, if you, one thing I didn't mention about the star operation is that usually with a star operation, you say that the star operation, if you apply it twice, you get back to the identity. It's an involution. So here, if you demanded that, you would find that j squared was equal to plus 1. That would imply j squared was equal to plus 1. So the fact that j squared is equal to plus or minus 1 is really saying that apparently, and this is if you want an awkward point, but anyway, it is what it is. It's saying that in our formalism, the star operation has the property that j to the fourth is equal to plus 1. So j squared can be either plus or minus 1, and that choice is the choice epsilon here. Epsilon prime, well, see, epsilon prime arises because in the algebra omega A, the operator d has some interaction with the star operation. So if you take d of an m-form star, that's equal to minus 1 to the m plus 1 d of omega m star. In other words, if you pull the star outside of the d, you either pick up a plus or minus sign depending on whether omega m is an odd or even form. Well, so now we extended d to, d was nothing but the extension of d to act on omega infinity. But you have to ask, well, is an infinity form, is infinity odd or even? Not clear. I guess you have a free choice. That free choice is this parameter epsilon, okay? So the oddness or evenness of infinity in this framework, the parity of infinity, signed to infinity, is nothing but minus epsilon prime. But then there's another way to detect the parity of a form, which is that you can commute it with gamma. So if you commute an m form with gamma, in the usual case, you pick up minus 1 to the m. You get a sign that depends on whether it's an odd or even form again. Oh yes, sorry. That's a very good point. So I wanted to truncate. I should have said that better. At this point, I wanted to truncate the sort of results that come out just from assuming that B is star and associative. Beyond that, I want to say that there is indeed, you're absolutely right. I have to input a gamma that so far played no role in B. I'm just saying that, so that's sort of a next part of the story that's not part of the original previous argument. But I'm just saying that there's a nice reinterpretation of those parameters given here. And so just to explain that a bit further, because it actually relates to something we learned from your paper with Desena. So there's this sign, and if you apply this to the infinity forms, in other words to H, this sign is nothing but epsilon double prime. So again, epsilon double prime also detects the parity of infinity. So in the even case where you have a gamma. Now you might say, uh-oh, maybe there's an inconsistency here. Maybe epsilon detects one parity and minus epsilon prime detects a different parity. Well, turns out a paper by Dabrowski and Desena come to the rescue. In the even case, J is not uniquely defined. Okay, so if there's two equivalent options. So if I use a J and I compute epsilon double prime and epsilon prime and they don't agree with each other, well, it turns out there's an equally good J called J prime, which is just in the even case I can define, which is gamma times J. That leaves the sign of epsilon double prime unchanged, flips the sign of epsilon prime. So so in the even case, there's always one choice out of the two possible j's that gives a consistent parity to infinity. Okay, so now I'll just very quickly say, I'll just very quickly give you a heads up about what Shane is going to describe. Shane is going to tell this whole story that I had alluded to. This will just be 1 minute. Shane will tell the story that I alluded to. First of all, that how do you get, a great part about Kahn's approach is that you take D and you fluctuate it, you add connection terms to it, but those connection terms give you both the gauge bosons and the scalar fields in one go. Here the interpretation is that what you're doing is simply making D covariant with respect to the automorphisms of B. And I'll show you how that goes when you apply it to the standard model. In particular, you get back everything you thought you should get in the standard model about charge assignments and particles. But you get one additional symmetry, this extra U1B minus L that I mentioned. And you get two more predicted particles, the gauge boson associated with this, and a new scalar field, complex scalar field sigma, which carries B minus L charge. I want to emphasize this is a phenomenologically viable model. It's interesting because, like Christoph emphasized, there are problems with the pure standard model, cosmological facts it cannot accommodate, that we believe, although this is a matter that this exact model had been previously considered, this exact extension of the standard model had been previously considered for its cosmological uses. Let's see, maybe the last sentence. I'm sorry, I know I'm over. Oh well, let's see. I didn't get to tell you all the problems and open questions. Anyway, the Higgs mass and Weinberg angle problems, that Christoph mentioned, still problems. Although in the sense that sigma has previously been introduced to solve the Higgs mass problem, it very likely solves it in exactly the same way here, because in a certain gauge, this thing, it looks very likely that it solves that same problem, but Okay, sorry for running over, I apologize. Anyway, it's very interesting, of course, to figure out what the relation is to these other approaches. Okay, thanks. That no, like in the standard model, it's not. And no, in fact, I don't know. In general, I guess so. In the standard model, it turns out there's only one more independent one. So that's exactly what Shane will talk about. Another of the open things I didn't discuss. So is that as I say, B can be associative or not associative. If you take it to be associative, you get back all the axioms and then this one additional constraint. This one additional constraint that helps you in terms of the finite geometry of the standard model. The Clifford, the canonical spectral triple satisfies the rest of those axioms, but does not satisfy the higher order conditions because left and right action by one forms don't commute with each other. So it's non-associative. So B is non-associative, which is okay. And so one thing, I don't know if Shane will have time to say it or not, but that's exactly another thing is that when you do this process, you fluctuate with respect to the automorphisms of that non-associative algebra, B, the Clifford algebra acting on H, the algebra B that you get from there. you get as a fluctuation d goes to d plus spin connection, the usual connection that you add to d. You can still compute the automorphisms well, you fluctuate the spin connection. That's just something that's not clear to me, is what the relationship is between. That's what we don't really understand yet, is what the relationship is between that and fluctuating that.